You know, when you get down to the smallest scales of reality, the rules we take for granted, the rules of energy, heat, and work, they start to get a little weird. We're diving into the world of quantum thermodynamics. It's a real frontier in physics, and it's making us rethink everything we thought we knew about how the universe works. And it all kicks off with one deceptively simple question.
So, this is it. This is the question that a recent study from the University of Granada decided to tackle. And it just sounds wrong, doesn't it? I mean, you'd think if you put something in a hot bath versus a cold bath, the process would be more or less the same, just in reverse. But nope. At the quantum level, it's not symmetrical at all. And figuring out why is unlocking some really profound secrets.
And look, this isn't just some quirky little factoid for a physics textbook. This question is like a thread. And when you pull on it, our whole classical understanding of energy starts to unravel. It's sparking a huge rethink, and it's got implications for literally everything, from the tech we're trying to build to how we understand reality itself. All right, so to really get why this is such a game changer, let's do a quick refresher on the old rules, the ones we all learn in school, the ones that run our everyday world. In the world we can see and touch, the difference between heat and work seems super obvious. Heat is just chaos, right? It's the random, disordered jiggling of atoms, like a molecular mosh pit. But work is order. It's energy with a purpose, a coordinated collective push, like all the molecules in a gas working together to move a piston. For a long time, that was the whole story. Simple, neat, and intuitive. But what happens when you zoom in? I mean, way, way in. Down to the level of a single particle, a single quantum bit. Well, that's where this beautifully simple picture completely falls apart. The place where all this weirdness happens is the qubit, the basic building block of quantum computers. A qubit isn't just a 0 or a 1 like in your laptop. It can be in a superposition of both at the same time. And it's in that strange state that the line between ordered energy and disordered energy gets impossibly blurry. Okay, check this out. This is a Bloch sphere, and it's a fantastic way to actually picture a qubit state. Think of every single point on the surface of the sphere as a unique quantum state. And a super important property that defines this state is something called coherence. It's like an orderly, synchronized dance between the 0 and 1 states. Now hang on to that word, coherence. It's pretty much the hero of our story today. So all this bizarre behavior created a huge puzzle for physicists. For a long time, the standard way of thinking, the standard paradigm, just tried to shoehorn these quantum effects into the old rules. But it just didn't quite work. The math kept spitting out inconsistencies, so that led to a new idea, an alternative paradigm that asked, what if the problem isn't the quantum effects? What if the problem is our old definitions of heat and work? And here is the crucial point. This alternative way of thinking doesn't just tweak the old definitions a little bit. It actually uncovers an entirely new source of useful, ordered energy that was hiding in plain sight the whole time. This quote from Andres Vallejo's thesis just nails it. That quantum coherence we talked about, that orderly dance on the Bloch sphere, the alternative view argues that's not just some weird quantum state. It's a form of work. It is ordered, useful energy that the standard model was just lumping in with chaotic heat. It was being totally misclassified. So, the new solution is actually beautiful in its simplicity. It's a 3-step fix. First, you have to recognize that quantum coherence is part of the system's total energy. Then, step 2, since coherence is an ordered state, you have to correctly classify its energy contribution as work, not as heat. And bam, step 3. Once you do that, the inconsistencies just vanish, the math works, and you get a much clearer picture of what's going on. Okay, so we've been pretty deep in the weeds of theoretical physics, but why should you care about this abstract debate? So what? Well, it turns out the real-world implications are absolutely enormous. This new way of thinking about energy has a direct impact on at least 3 massive areas: the future of computing, our ability to model our own planet, and, get this, even our fundamental understanding of why time flows forward. Let's start with technology. Building a working quantum computer is one of the biggest races in science right now. But the whole thing depends on keeping those qubits stable and coherent. And that means keeping them ridiculously cold. So as the Granada study showed, if quantum systems heat up faster than they cool down, that's a fundamental problem we have to design around. This research isn't just theory, it's a practical guide for engineers.
Now for the really big picture, science. This research ties directly into the field of complex systems, which, by the way, won the Nobel Prize in Physics back in 2021. So what is a complex system? It's basically any system where a whole bunch of small parts interact, and from those interactions, large-scale phenomena just emerge. Think of a flock of birds, the economy, or the global climate. You've probably seen this iconic image before. It's the Lorentz attractor, and it's the perfect visual for a complex system. It shows how simple, deterministic rules at the micro level can create these incredibly complex, chaotic, but beautiful patterns at the macro level. The weather is the classic example. A tiny change in the starting conditions can lead to a completely different outcome. And it turns out, the tiny rules that govern energy at the quantum scale, those are one of the critical starting conditions for the biggest complex system we know, our planet's climate. And that right there, that's the crucial link. The global climate is an unbelievably complex system. To make accurate models of it, we have to get the fundamental physics right, all the way down. If our models are accidentally classifying useful quantum work as chaotic heat at the molecular level, those tiny little errors can cascade upwards, leading to much bigger, inaccurate predictions on a global scale. Getting these micro rules right helps us build better models for the macro world that we all live in.
It's just incredible when you think about it. This whole journey started with a simple question about heating and cooling, and it led us to redefine the very nature of work and heat with real consequences for our technology and our planet. It really makes you wonder, if our understanding of thermodynamics was this incomplete at the quantum level, what other fundamental laws of the universe are just waiting for their own quantum revolution?